talked about enthalpy. So enthalpy is kind of, you can think about it as the energy that is stored, potential energy that's stored within bonds. And when bonds are broken, that energy comes out. When you form bonds, you need to use up energy to do that. And so sometimes when you're doing a chemical reaction, energy comes off as heat, and that would be an exothermic reaction. Sometimes energy goes into a reaction. Hi, welcome. Sometimes energy goes into a reaction and it gets used up, and so that would be an endothermic reaction. So that's kind of like a cold pack that you might have. But is Ellie not coming?
No, she's in Florida.
Oh, okay. Here, let's give you know what, she told me that last week, but I didn't write it down, so I forgot. All right, this is for you. And if you have anything to turn into me, that'd be great. Okay, so, all right, so last week we did talk about when you have a problem, you would figure out what balanced chemical equation, you would build them, and then you would count all of your bonds, and you would use table 13.1 to figure out the bonds that are broken, and then subtract all the bonds that are formed to find out how much enthalpy is given off or used up in that reaction. Remember, if you have a negative enthalpy, that means heat is coming off. And usually those reactions go much easier than reactions that have a positive enthalpy, which means you'd have to put energy in to make the reaction go. So it's easier if heat is coming off or energy is coming off. So what I kind of mentioned last week, speaking of Ellie in Florida, when she goes down to Florida, maybe she drives one way, and when she comes back, she might drive another way. Either way, she's going to start here in Columbus, and she's going to end up in Florida. So it's might be a different path, but the overall effect is that she gives there. And Hess's law is what we're going to use today. Hess's law says that enthalpy is a state function, and that means it's independent of path. So no matter how you get around there, which bonds are formed, which bonds are broken, the overall getting there, doing the reaction is going to be the same depending on the item that you're working with. And so if you're going to use Hess's law, it's a lot easier because you don't have to build each molecule and count the number of bonds. Someone has figured out the enthalpy for every molecule. So if you look on table 431, these are called standard enthalpies of formation. So they have these delta H sub F, and then it's this little zero up at the top. That's the enthalpy of formation. So that means someone already did the work to figure out how much energy is in that molecule. They already counted all of the bonds. And you'll notice that each of these substances has, if it's a gas or a liquid or a solid. So the other way, when you were counting all of your bonds, didn't take that into consideration. And that makes a difference. So actually, this way, not only is it easier, it's more accurate because it takes into consideration solid, liquids, gases. So easier, more accurate, to me better. All right, so we like using Hess's law for enthalpies of formation. So the way it's figured out then is that you can do the delta H, again, why is H enthalpy? I don't know. They picked a letter and they plopped it in there. Is of formation, so again, it's got this little zero, so that means use a different chart. Use the chart on 431. I tell you right now on your test, you will have to do the long way using chart on page 424, table 13.1, bond energies. You will have to do one problem with that. I apologize. But you're going to have to know that this way's better. One, it's easier. Two, it takes into consideration solid, liquid, gas. So it's more accurate. So it's enthalpy or formation, and that equals the sum again. So it's this sign that you'll use a lot in calculus. The sum of, it just means add everything up, of the delta H of formation, of the products, minus the sum of the enthalpy of formation of the reactants. So before we did reactants minus products, now we switch it. So that's a little confusing, but why do we do that? It's because they've already figured out this new table for you, and it's easier, so just go with it. So you're going to add up all of the products and subtract all the reactants. Okay. All right, so let's do, I should stick to my notes this time. Also, the standard enthalpy of anything in its elemental form, like hydrogen in its elemental form, or oxygen in its elemental form, if you would use it like you would find not in a molecule, but the enthalpy of formation, if you're not finding it on your chart, probably it's like you would find it on the periodic table, and the enthalpy of that is 0. How that all works, again, that would be a much deeper, now I just say yes, that's how it works. It works. If you have an enthalpy of formation of an elemental thing, it's 0. So when you're adding, I can add 0 super easy. So let's do a problem. The standard enthalpy of formation of an element in its elemental form is 0. So let's do example 13.3 on page 432. So again, we're going to add up all the products and subtract all the reactants. So now we're using Hess's law, and so we're doing products minus reactants. Okay, so what is the enthalpy, delta H of formation? So that tells me right away that I'm using chart 13.2 on 431. Of the following reaction, we have, I should do this, 2NO in its gaseous form. Remember, now we're taking into consideration solid, liquid, gas. Plus, my marker should work, 0,2 gas turns into 2NO2, and it's a gas. Okay, so we're going to do the products minus the reactants. So we're going to go to our chart, and we're going to say, we don't have to build it now, we don't have to count bonds now. We're going to say this is my product, so we have 2 moles of this. I get my number, instead of counting things, I get my number here from this is a 2, this is a 1, this is a 2. And we have 2 moles of NO2 gas. So we're going to look up NO2 gas, and it's 33.2. Unit is kilojoules per mole, and we're going to, that's all of the products, minus, now you might have to use a parentheses, 2 moles of NO gas, so again we're going to do 2 moles and then times, find NO gas, and that's 90.3 kilojoules per mole. And then O2 gas, 1 mole of that, and I look and I don't find it on my chart. Oh, that's right. O2 gas is an element, right? So that's how I find it in nature. That's on the periodic table. It's really O, but there's 1 mole of that, so I can add 1 mole of 0, which means it drops off, right? So I can kind of ignore that, but you can write it if you want to remember what you're doing. So I'm going to do 2 times 33.2 minus 2 times 90.3. If you can't use your parentheses on your calculator, make sure you do 2 times 90 first. Write down your answer, 180 something. Write 180.6. Kilojoules per mole, this is mole times kilojoules per mole, so your moles cancel out. So you're left with kilojoules. So you should get, if you put it in your calculator right, a negative 114.2 kilojoules, because this is 2 times 33.2, so 66.4 kilojoules minus 180.6 kilojoules gives me a negative 114.2 kilojoules. What does that mean? That means that energy is coming off of this reaction. If I have a negative delta H, it's exothermic reaction, heat is coming off. So if I mix these two things together, is that reaction probably going to go on its own? Yes, and it's going to be hot. Heat's going to come off. Okay? So if it says, is this an exothermic or endothermic reaction? Negative tells me it's exothermic. Okay? So is this easier than drawing them, counting bonds? Yes, it is. We say thank you, whoever made up this chart, and just remember that now you're doing the products minus reactants. Okay, so it's kind of switched. All right, some gas companies put a small amount of liquid ethyl alcohol in their gasoline tanks. What is delta H for the complete combustion of this chemical? Oh, wait, they didn't give me the reaction. So I'm going to have to remember what is combustion. So remember, combustion means add oxygen and you end up with carbon dioxide and water, right? Combustion means fire. Guess what? It's probably going to be exothermic, so you better get a negative delta H. So if we have to do this, we need to have a balanced chemical equation. So okay, or I'm not going to dive under the table. C2H6O. And it told me that it's liquid ethyl alcohol, so that's a liquid. Remember, if we're using this chart, we need to know if it's solid, liquid, or gas. And it's combustion, which means add oxygen, and you come out with carbon dioxide, and water. So, do I have a balanced equation? No, I don't. So I'm going to have to remember how to balance an equation. There's 2 carbons here, so I'm going to need 2 carbons there. If you want to make the little charty chart and CHO and CHO, we haven't done this in a really long time, so I'll do it just to practice. I have 2 carbons and 6 hydrogens and 1 oxygen here and 2 here and 1 carbon. Before I did that, I have 1 carbon and 2 hydrogens and 2 oxygens and 1 oxygen. So to balance, I'm going to make that a 2, which makes that a 2, and this is a 4. Did I lose anybody yet? Hopefully you remember this. Balanced, H is not balanced yet, so I'm going to have to put a 3 here. That makes that a 6. That makes that a 3. So that makes 4 and 3 is 7. So I need to have 3 of these to give that a 6, and then that's my 7th. Am I balanced? Yes, I am. Okay, so now that I'm balanced, that was the hardest part. Now I'm finding delta H. So I'm going to use the delta H of formation. So I'm going to use the chart on 431, and I'm going to do products minus reactants. So products first. So I'm going to find 2 moles of carbon dioxide, and hopefully you know if it's a solid, liquid, or a gas. This is a gas. And if this is combustion, this water is going to be a gas because it's hot. So gas and gas. So products of carbon dioxide gas is going to be negative 394 kilojoules per mole, plus 3 moles of water, and water is going to be a gas, so it's negative 242 kilojoules per mole. And this is all together. So again, if you write out your problem and I can see your numbers, probably the math here is just going to be an order of operations problem. You need to do 2 times this plus 3 times this, use parentheses. Maybe put your answer here. And then subtract the C2H6O, and it's a liquid because they said that in the problem. So it's going to be 1 mole of that. So it's going to be, and it's subtracting that. So minus 278 kilojoules per mole plus 3 moles of that, but we did the same problem last time, and O2 is elemental form, so it's not on my chart, and that means it's a 0 because it's an elemental form. So you could do minus 3 times 0, but I'm too lazy to write it, and I ran out of space. So just remember, this is a minus number here. Sign's going to throw you off too. So it's 2 times negative 394 plus 3 times negative 242 minus a minus 278, which means I'm adding this together, right? Plus 278 kilojoules per mole, right? So minus a minus gives you a positive. So if you do the math correctly in your calculator, 2 times negative plus 3 times a negative, use your parentheses, plus 278, you should get a minus 1,236 kilojoules. And these are exact. Why are they giving me, I would round it. So, this is 3 significant digits, this is 3 significant digits, this is 3 significant digits. I would only get, but I'm rounding to my least significant place. So, so when I'm adding and subtracting significant digits, I round to my least significant place, which is this place, and this place, and this place, and that's where it is. I have more significance here, but I really don't because it's still rounded to the same place. Okay, so this has 4 significant digits, but it's rounded to the same place. If I would have multiplied it, it's different. Then I would only get 3. But because I'm adding and subtracting, I'm rounding to this place. Okay? Did I lose anybody? So, what did we learn so far? This way is so much easier. Make sure you use the right chart. Elemental forms are 0. Yes. Products minus reactants. The other chart, build it, count all your things, use reactants minus products. Okay? All right. What else? All right, so did I do 13.4? Not really. I'm going to skip 13.4. If I have time, I'll come back to that. I'm going to skip to energy diagrams, which is on page 436. These, again, to me, I think it's more of a physics thing than a chemistry thing, but maybe not. But they're not hard, so yay. Okay, so here's the thing. When I am doing a reaction, like C2H6O plus hydrogen gas, it turns into C2H6 plus water. Okay, so for this reaction, I want to know how much energy is going to go into this. So this is an energy diagram, and how much energy is coming off of it. So usually when they do these energy diagrams, they're going to have the energy here. So how much energy is going in, and this is it's by time really, but they have the energy coordinate down here. So So this is my things that are mixed together. There's always a little hump here, and then if energy is coming off of the reaction, or if energy is going into the reaction, it will look a little different. So this part here is called the activation energy. So in other words, maybe when you're mixing something together, maybe that's when you're stirring it together so you get them to react. There's always some way, I mean, how do you get together with your friends, right? You need some place to come together and get some, maybe a get to know you game, right? To get you to react. And then maybe there's a lot of reaction, or maybe there's not very much reaction when kids get together. I don't know. So this is the energy that it takes to bring you together, sort of. And it's called your activation energy. And we'll talk next time about how to make that smaller, because the smaller that is, the easier the reaction takes to get going. So this is the activation energy. So if you have the distance between here, I'm trying to look at this one, and here, this difference is going to be your delta H, the energy that goes into making your reaction. So if you have, I should review this. Okay, so if you start high and you end low, you're going to have a negative delta H. That means energy came off of your reaction, right? So here on this one, this is at 100 kilojoules. It goes up to 120 kilojoules. And then when it finishes, it's down at, I don't know, maybe 50 kilojoules. So they'll say, is this, I forget how they word the questions. They'll maybe say, what's the activation energy? You would take 120 minus 100, and you're going to have to add, so that means I put 20 kilojoules into this to make the reaction go. But I started at 100 and I ended up at 50, so that means that I had 50 kilojoules of energy come off of it, right? Because a negative H means you have energy coming off. So this, if I start high, kind of ignore the activation energy, but if I start high and I end low, I have a negative delta H. That means I have an exothermic reaction. And will my reaction go? Probably it will, because it doesn't take as much energy. If this is not very big, it should go easy. It should make the reaction go or start very easy. And if more energy comes off of it, it's a reaction that probably is a spontaneous reaction. But other reactions, they're going to give you a bunch of different energy diagrams. And maybe they start at 100 kilojoules here, and they go all the way up, and then end at, I don't know, this is 800, maybe this is 500 here. So if it starts at 100, it has a really big hump here. That means it takes a lot of energy to get that reaction to go, and it ends at 500. So that means I have to put a lot of energy into this reaction, and it uses up more energy than I started with. So I have a positive delta H. That reaction would be an endothermic reaction. That wouldn't be very easy. It takes a lot of energy to make it go. Now maybe I get gold or something out of it, so I would want to do the reaction. It'd be worth it to do it. But probably it's going to be a really hard reaction to go. Or maybe they give you one that starts at 100, and it goes up to 600, and then ends at like, I don't know, 125. Okay? So they're going to give you some energy diagrams, and they're going to say, which is the easiest reaction to go? Well, the easiest reaction to go is the one that has the smallest activation energy. So you look at your hump from where you start to where you, and they're evil, so they're not going to make them so that they're all the same size. You might have to subtract, right? Go from 50 to 120 or 100 all the way to 800 or 100 to 600. Which one's easiest to go? The one that has the smallest activation energy is the easiest one to go. They maybe say, which one is an exothermic reaction? Well, if you start high and you end low and you have a negative delta H, that's going to be your exothermic reaction. Or they'll say, which one's your endothermic reaction? Well, any that start low and end high, did I say this backwards? If you start high and end low, that's negative. If you start low and end high and you have a positive delta H, that's going to be your endothermic reaction. It uses up energy. So endothermic, exothermic. Which one's the easiest? The one that has the smallest hump. Okay? So they'll give you like 3 different charts, and they'll say which one is the easiest to go. You just have to, if you practice on example 13.5, let's just look at those real quick. So flip to 438. And here this one starts at 100. See how they don't have any of them the same. The first one goes from 0 to 150, the second one goes from 0 to 60, and the third one goes from 0 to 60. So you might have to subtract to make them to be the same. To compare them, I should mean. So this one starts at 100. It goes up, I don't know, to 125-ish, and then comes down to maybe 50. So this hump here is the activation energy. And from here to here, so is that going to be a positive delta H or a negative delta H? Negative. This second one is a different, so this one only goes to 60 up here, so this one goes to 50. So it starts at 20, and it goes all the way up to 50, and then down to 40. So, so from 20 to 50 is maybe 30 kilojoules up to here. From here, oh no, we started here. From 100 to, I don't know, maybe this is 120. This is 20 kilojoules. So they don't look the same. This one looks like it has a bigger, maybe this one looks like it has a bigger hump. It does. This hump is only 20 kilojoules. This hump is 30 kilojoules. So which one's going to be easier to go? The one with the smaller hump, right? But the numbers aren't the same, so just don't get thrown off by that. So is this one an exothermic or an endothermic? Endo. It starts here, low, and ends high. So I have a positive delta H. So endothermic, exothermic. Okay? And the last one starts at 50, goes up to maybe 60, and comes down to 20. Here's 20. So of these two, which is the easier reaction? Well, from 50 to 60 is only 10 kilojoules. So this one's easier to start. Which one's exothermic? They both are. This one's still exothermic. You still start high and end low. This one you start high and you end low. This one gives off 30 kilojoules of energy. This one gives off 50 kilojoules of energy. So they're both exothermic. This one gives off more energy. But this one's easier to start. So, anyways, there you go. Energy diagrams. Okay? And at this point, we switch to something called, the other one was enthalpy. And again, it's kind of the energy that's in a reaction, or comes off of a reaction, or is stored in the bonds of a reaction. Enthalpy. That was delta H, enthalpy. Now, we're going to talk about S. Again, why S? I have no idea. S is your entropy. this one is kind of like energy. It's not exactly energy, but you can kind of think of it as energy because it's measured in kilojoules. Entropy, on the other hand, is disorder. So if you went up into a certain one of my children's bedrooms, you would see a lot of entropy. I just closed the door, right? So entropy is disorder. So in this figure 13.3, you have a nice fireplace with little flowers there, and it's all nice and ordered, and so that would have low entropy. It's very ordered, right? But then once the flowers fall and the flowers are strewn everywhere, that would have high entropy. It's just the amount of disorder in a system. The second law of thermodynamics says the entropy of the universe must also increase or remain the same. It cannot decrease. And this is, as a Christian, is why here's a law of thermodynamics saying that things don't get more ordered. But that's exactly what evolution is. You took some pieces of stuff and you all of a sudden put it into some sort of design and it got more complex. Physics, chemistry tells us this doesn't ever happen. We never see it happen. The law of thermodynamics means it's been tested over and over and over and over and over, and it doesn't happen on its own. You have to put energy into a system to get ordered. If I tell my kid to go clean his room, that takes a lot of energy to put it into some semblance of order, which is why I close the door and I walk away. Okay, so disorder happens on its own. Okay, especially if there's more stuff there, right? If you're a hoarder, your disorder can get out of hand, right? And then, I mean, goodness gracious, you need to call and burn the house down. It's just easier, right? So if you have a lot of stuff or a lot of particles or a lot of molecules, the more molecules you have, the easier it is to get more disordered, right? The fewer you have, it can still get disordered, but it's easier to clean it up, right? Which is why probably your mom says go through your room and get rid of all the stuff that you don't need, because the less stuff you have, the easier it is to keep it clean, right? So the solid state has the least amount of entropy. Why? Because if I have the table or something I can touch, or even a solid piece of water, those molecules are in some sort of structure such that they can hold together and they're solid state. So they are holding together and they're maybe crystallized somehow, so it has less disorder. But a gas, heat up that, right? It turns into a liquid and the disorder starts to happen. The molecules are moving around. You get into gas form and those molecules just jump everywhere, right? So solid has less disorder, liquid has a little bit more, and gas has the most disorder, right? The entropy, or the disorder of a system, increases with increasing temperature. Again, solid has less, gas has more, gas has the most, so if I increase the temperature of water, it's going to turn from a solid to a liquid to a gas. So the more heat I have, the more disorder I have. And the entropy of a system also increases as the matter increases. So if I have a lot of gas particles, the disorder is a lot more, or a lot of socks or underwear or whatever. The more stuff you have, the more your disorder can increase, okay? And so disorder, entropy, is marked, is just positive or negative. So positive means more disorder. Negative is less disorder. Okay, so let's look at example 13.6. If I have zinc, and it's a solid, plus HCl, hydrochloric acid, and that's aqueous, so again, kind of a liquid, turns into zinc chloride, which is an aqueous, and hydrogen gas. And they say, for the reaction below, determine the sign of S. So is it going to more disorder or is it going to less disorder? They just want you to do a plus or a minus. So here I'm a solid. I kind of think of it, I don't even really look at what they are. But I have 1 mole of a solid plus 1 mole of kind of a liquid. Aqueous is kind of like a liquid, turning into 1 mole of a liquid plus 1 mole of a gas. So I have solid and a liquid turning into a liquid and a gas. So is that getting more disordered or less disordered? Who wants to take a guess? More, because solid is less disorder, gas is more disorder. So if I'm going from liquids to gases or solids to gases, again, you don't even necessarily have to look at what's mixing together. Look at their state of matter, okay? And how many moles of it. If I have 3 moles of this turning into 1 mole of this, that would be close, right? Because this is a lot more order. Well, I guess it would still be a positive because I'm still turning to a solid to a gas. But I look at the numbers of my stoichiometric coefficients, the big numbers, and I look at my states of matter. So this one, B, is nitrogen gas, and it's mixed with 3 hydrogen gases, and it's turning to 2NH3 gas. So this is kind of 1 gas and 3 gases turns into 2 gases. So is that getting more disorder or less disorder? Take a stab at it. It's positive or negative. More disorder is positive, less disorder. So I have
like the same though, because they're all gases.
They're all gases. So now we have to look and remember, the more molecules I have, the more disorder I have. So I have 4 gases over here and only 2 gases over here. Which one has more disorder? This one. So this one is going to be a negative S because it's getting more ordered. So less disorder is more ordered. So what does that mean, really? It's going to take a lot more energy to do this because things don't get more ordered on their own. It takes energy to do that. Okay? Let's do this last one. Let's switch colors because I think it's red hard to see. I'm not even going to write what it is. 2 moles of this solid plus 1 mole, what is that? Barium with a bunch of water, plus 1 mole, but it says it's a solid, turns into 1 mole of a liquid, aqueous is like a liquid, plus 2 moles of a liquid, aqueous, plus 8 moles of a liquid. Is that getting more disordered or less disordered? Going from solid and solid to aqueous, which is a liquid, and a liquid.
More?
It's getting more disordered. So is my S going to be positive or negative? S is going to be positive. Very good. So remember, S is disorder. Entropy is disorder. If it's getting into more disorder, that's easier to do, so you have a positive S. Does that make sense? Okay. Now you can calculate this. So all substance, even elements, have absolute entropy. So last time we were able to calculate enthalpy. We can also calculate entropy. And it's the same sort of formula. So really, if you remember, enthalpy is going to be the sum of the products minus the sum of the reactants, if you're using Hess's of the enthalpy of formation, right? It's products minus reactants. Well, entropy is going to be the same sort of thing. you're going to want to do the products, the sum of the products minus the reactants. They're still going to give you a chart. This time though, this one you had elemental forms were 0, but in entropy everything has disorder. So there's no elemental forms are 0 for this one. So let's see, is there a problem here to do? So this one is the table for entropy is going to be on page 444. So they're going to have, I don't see a problem here that they're having us do. But it's basically the same thing. They'll give you a balanced equation. You'll have to do the entropy for all of the products and then add them up, and then subtract all the entropies for the reactants, add them up, and see if you get a positive or a negative. Okay, but just remember your elemental forms aren't 0. So it's the same sort of thing. And if that wasn't enough, I have 15 minutes. So enthalpy, entropy, you've probably never heard of these things before, so I'm going to get to throw one more thing at you. So this one is called Gibbs. Let's use a new color. Gibbs free energy. What's Gibbs free energy? Gibbs free energy is, will this reaction go? So I mix these two things together. Are they, and I know like what I want them to turn into, but if I mix them together, do I have to add heat in there? What's going to happen when I mix them together? Is the reaction going to go? Because remember, we had those cool little charts where it has this activation energy and then tells me if heat or energy is going to come off, or if I have to put energy in, or if there's activation energy that is a really big hump that's going to take a lot of energy to make the mix. Gibbs free energy is a way to calculate, is your reaction actually going to go? And it takes your enthalpy and your entropy into consideration. So is it going to go or not? So let's see if I can find on here. So Gibbs free energy is how you mix all these things together. So Gibbs free energy is delta G. That kind of makes sense, right? Entropy I don't think makes sense. S. Enthalpy I don't think makes sense. It's an H. I don't know, but Gibbs does kind of make sense. Okay, so your delta G, delta doesn't look like a delta. Your delta G is your enthalpy, delta H, minus temperature times your delta S. What does that mean? So if I want these two things to mix together and actually react together, I need to figure out how much energy is going into it and if I'm getting more ordered or less disordered. And why does temperature factor in there? Because temperature affects if I'm getting more ordered or less ordered, right? If I'm going to turn into a gas, it's going to be more disorder. If I'm freezing, it probably is a solid and I'm going to have more order or less disorder, okay? So that's why temperature has to factor in there. So there's another chart of Gibbs free energies. And here's the thing, if you remember your enthalpy and entropy, they really have the same, it's still products minus the sum of the reactants. Again, so again, there's another chart. So the chart on page 447, you might want to remember that that is happening at 298 K. It doesn't tell you that, but it is happening at 298 K. I wrote that down, so you must need to know that for something. All right, so it's still, you're gonna calculate the Gibbs free energy, you subtract it, you get a balanced equation, you figure out your products minus your reactants, and this time you use chart 447. So really, these sound like three completely different things, but they are related. There's a chart for each of them. Make sure you use the right chart. Make sure you're doing products minus reactants, except for the first time that you're doing enthalpy, which is the opposite, where you're doing all of the bonds. Why do I care about Gibbs free energy? Because Gibbs free energy tells me, will my reaction go? If my delta G turns out to be negative, if it's a negative, if it's negative, my reaction will go, right? I'm just double checking that I'm not telling you wrong. If my delta G is negative, then it will go. Why? Because I want my delta H to be negative, so energy is coming off. And if this is more disorder, that's positive, and I'm subtracting that, so I'm going to get a negative and a negative. So I want my delta G to be negative, because if this is negative, my energy is coming off and it'll go. If this is a positive, that means, so this I really, if my entropy is positive, I'm getting more disorder. That happens on its own. If this is negative, I'm getting energy off. So if I have a negative minus a positive, so this will definitely go. But if I have a delta G that is positive, it will not go. So in other words, if I mix these things together, they sit there forever, nothing ever happens. So it's not going to turn into what I want it to turn into. So, let's see, let's do one. Yay. Oh, and also, elemental forms for this one are also 0. So if you're looking in your chart and you're like, I don't see this, elemental forms for this are 0. So you need to worry about elemental forms for entropy, but you don't need to do it for enthalpy or Gibbs free energy. All right, this is page 448, example 13.7. We study the following chemical reaction. Actually, I have a feeling I'm going to need space. So, 2, why does this work sometimes and not other times? Right? All right, 2 NO, and it's a gas, plus oxygen, gas, turns into 2NO gas. We found that its delta H sub 0 was negative 114 kilojoules. And its delta S sub 0 equals negative 147 joules per mole Kelvin. What is its delta G at 532 degrees C? Oh, good. They calculated it for me. That is 805 Kelvin. So whenever we're doing these, we have to have them in Kelvin anyways. And then it says, so that's one question. And then it says, is it spontaneous? That means, will it go? So will it go? Well, if we get a negative delta G, it will go. If we get a positive delta G, it will not go. Okay? So we need to decide if it's a negative or a positive. All right? So our formula for delta G is the sum of the products minus reactants, sum of the reactants, So we need to look at the balance equation. So product is 2 NO2 gas. You flip to the little charty chart, make sure you're looking at the right one. NO2 gas is 240. So I have 2 moles of that. So I'm gonna have 2 moles of, why don't I have what they have to do? No, they didn't even do that. They just did, oh, they didn't even have you calculate that. They just want you to do delta G equals, what is it? Delta H, they already figured it out for you with your H and your S. Minus temperature times your delta S. So you're going to figure out your delta H, what they gave you is negative 114 kilojoules, minus temperature, they told us was 805 Kelvin, times my delta S, which they told me was negative 147 joules per mole Kelvin. Here's the problem, I have a kilojoule here and I have a joule here, so my units aren't gonna work out. So this Kelvin's gonna cancel that Kelvin, but this needs to be switched from joules to kilojoules. So if you don't know how to do that, 147 joules, remember there's 1,000 joules in 1 kilojoule, so that means I'm moving my decimal place 3 places. So that was the hardest part of this one. So once I'm in kilojoules now, it's order of operations. Negative 114 minus, make sure you do this in parentheses, 805 times negative 147, and you should get a positive delta G equals positive 4 kilojoules per mole. So that's the one question is, what's your delta G? Your delta G is 4 kilojoules per mole. Is it spontaneous? Well, to be spontaneous or to go, I need to have a negative G, and I don't. I have a positive G, but it's close. So the next question says, is there any temperature at which the reaction does work? Can I heat it up enough that it will actually go? Well, yeah, you can. So let's see what that would be. So, all right, so let's see. I mean, if you heat it on the sun, anything will go, right? But, all right, so to go, I would have to, because delta G equals my enthalpy minus temperature times my delta S. So I need this to be less than 0. I need it to be a negative number. So how would I do that? I would take, I just erased all my numbers, negative 114.2 kilojoules per mole minus the temperature times, what was it, negative 147 kilojoules per mole times K, and that has to get me a negative number, less than 0, okay? So I have to solve it for T such that T is a negative number. So I'm going to get, how do I do that? I've got to get this to the other side, so I'm going to do, is it easier to bring that one over there or that one over there? So they did T times that is less than, I'm going to add 114.2 minus that. I just get confused on my math here. So I need to add that. That means that this, I do so much better with actual numbers than negative zeros. T times that is they flipped the sign. It's less than 0. So I'm going to rewrite negative. That's why, because they switched the sign there. Okay. So they're adding 114 to this side, but then that left that with a negative number, so I'm just going to switch my numbers. So T times 0.147, but that's still a negative number, kilojoules per mole, is less than 114.2 kilojoules per mole. So I'm going to divide that by 0.147, which means I got to divide that by 0.147. So my T has to be less than whatever 114.2 divided by 1.147 is. So that's going to be 770 K. So if I heat it up to 770 K, which is really hot, my reaction will go. Would you ever do that? I don't know. Okay. The other problem on the end of page 449 is one where I was starting before, where you're doing the products minus the reactants. And remember that your elemental forms are 0, and that one is using chart on page 447. So then they figured out a number for G rather than using K and, S and H. Enthalpy and entropy. So you might, but it's similar to the other problems that I did with enthalpy and entropy. If there is a problem like this, if this was confusing to you, do it on your own, or make sure you do your review problems, because there is one on the test that you'll get a positive G and they'll say what temperature can you make it go, and you do kind of have to do this.